Let's talk about areas under parametric curves. Now, we've looked at areas in the past. Area we looked at in the past was like a definite integral, like the integral from a to b of f of x dx, like this. So this was a definite integral. Okay. And what we want to do now is we want to find the area under a parametric curve. So let's say we have a parametric curve and it has two coordinate functions, x equal to f of t and y equal to g of t. And let's say that our parameter ranges from alpha to beta. So this is how we can find the area under the curve. Okay, I will have a definite integral over here. Remember, usually we have f of x as our integrand. In this case, f of x is really the y value. So when I want to write the formula for this, the first thing I do is I could put an integral sign over here. I'm going to replace the y with the g of t. And I need to replace the dx. So what I'm going to do first is I'm going to differentiate the coordinate function x. So I have dx dt is equal to f prime of t. And then this means that I could rewrite dx as f prime of t dt. So I take that piece and I write that on the right side of my definite integral. So here's f prime of t dt, like that. And then finally, I really need to worry about the limits of integration here and here. Now, I don't want to put a and b because those were x values. So I really need to ask myself, what's the value of t when x is equal to a? Well, a is supposed to be our initial point, so I'm just going to start with my initial value of t, which is t equal to alpha. And then the b is going to represent our terminal point, so I can obtain x equal to b by plugging in beta in for t. So my upper limit of integration is going to be t equal to beta. All right. And this is my formula for how I find the area under a curve. So I'm going to highlight this formula. This is the area under the parametric curve. So let's take a look at an example next. Let's find the area inside this ellipse, x equal to a cosine of t and y equal to b sine of t. Now, we had talked about parameterizing an ellipse in the past. I just want to remind you of how this looks. So let me draw a quick sketch of a ellipse over here. And we're not going to find the area inside the entire ellipse. What we're going to do is we are going to find the area inside the top half of the ellipse, going from negative a to a. And let's say that this part here is b. So we know that our ellipse is going to look something like this. We're going to find the area of the top half, and then we're going to multiply that by 2. Okay, so the total area is going to be equal to 2 times. Now, let me for a moment pretend that this curve over here represented f of x dx. I'm going to put that in quotes, I guess. And normally it would go from negative a to a, right? But in our case, we know that the parameter that corresponds with negative a is going to be pi. Remember, we start at 0 and then we go around to pi like this. So actually the lower limit of integration would be pi. So I'm going to put a pi for my lower limit over here. And we're going to go to a. So in order to get this point a, that's when t is equal to 0. So I'm going to put it 0 for my upper limit of integration. Now we can see that we want to put our coordinate function for y inside for our integrand. So that's going to be b sine of t. I still need to replace the dx part. So let me calculate dx off to the side here in red. Dx is going to be equal to the derivative of a cosine of t, which is negative a sine of t dt. So let me pop that into my integrand, and we're going to get a negative a sine of t dt like that. Okay, so we see here that we have a few constants that we could factor out. Namely, I have a negative a and I have a b. So I'm going to pull each of those things out of my integrand, and I'm going to get, this is equal to negative 2ab times the integral from from pi to 0, and then we're going to have a sine squared t dt. Now, it kind of bothers me that the lower limit of integration is larger than the upper limit of integration. We know that we can invert these two things, and when we invert them, we pick up a negative sign, which is going to cancel with this negative sign here. So let me rewrite this guy as 2ab times the integral of from 0 to pi sine squared t dt. Now, this is the classic trigonometric integral where I need to use the half angle formula. So I'm going to have 2ab integral from 0 to pi. We're going to have a 1/2 times 1 minus cosine 2t dt. Here you can see that I'm going to have the 1/2 in my integrand. It's going to cancel out with the 2 in front. So I'm left with ab times the integral from 0 to pi 1 minus cosine 2t dt. All right. So we got our ab out in front. The antiderivative of 1 is just t. We're going to try to find the antiderivative of the negative cosine 2t over here. Let's do a quick u substitution off to the side over here. So we're going to let u equal to 2t. This means du is equal to 2 dt, or dt is equal to 1/2 du like this. So we know that when we make our substitution, we're going to have this extra factor of 1/2 out in front. Okay, so when I find the antiderivative of this, we're going to have negative 1/2 sine of u, but my u was 2t, so I'm going to put the 2t back here like this. And then we're just going to integrate this as we go from 0 to pi. So I'm going to make my substitutions. I'm going to get ab, and then we're going to have pi minus 1/2 sine of 2 pi minus, I'm going to put a quantity here, 0 minus 1/2 sine of really 2 times 0, which is 0. And sine of 2 pi is 0. Sine of 0 is also 0. So at the end, when we simplify, we're just going to get a times b times pi as our final answer. This is an area, so let's tack on a units squared, since no units are specified, and we'll highlight our final answer like so. All right, everyone, take care.